All right, so good morning. Welcome to day 3 of Math 105 Calculus. And today's an exciting day because we actually get to start doing calculus. Now that we've had a little bit of review of the more important topics from pre-calc, we're going to start diving into calculus. And the first thing I'm going to do with you is give you a little bit of a why calculus even came to be. Some of the questions that were trying to be answered that couldn't be done with just algebra and trig, which led to the necessity for something new. So we'll start there, and then we'll start working our way into the calculus. But I want to go ahead and just start. Any questions about homework? Anything we'd like to talk about from that? Okay, good. I'll take silence as everything's going okay. Obviously, this first homework set isn't due until Monday night at midnight, so we will meet again one more time. And you'll have opportunities to send me messages and email and all that. I did have a question. Somebody asked me about when I respond to your questions in the homework sets, like when it says ask instructor or whatever. I did look, and those emails get sent to your LTCC account, and I know that might not be your primary. I know it's not your primary, and you may not check it all that frequently. But if you are asking me questions through there, when I respond, they do get routed there. So make sure you're going in and looking at it, or probably best just to send, just have an automatic forwarding to your primary email. Anyway. Okay, well, then since there are no questions regarding homeworks or anything, we'll go ahead and go to the board.
All right, so calculus. Why calculus? First, let me just give you a little bit of history of calculus. This isn't super important for the exam or anything like that. This is just for your information. But calculus was actually invented. I know it's weird to think that math gets invented, but it does. It got invented actually independently by a couple of different people. I think the world was just ready for calculus. That's why these two guys came up with it at the same time. One of them you know well. I'm sure you've heard of him. He's kind of a biggie, easily top 3 mathematicians, scientists of all time. And that was Isaac Newton. So Newton was English, and he is one of the ones who came up with calculus. The other mathematician is one you've probably not heard of. Only people that are actually into math know this guy, mostly because he didn't do anything sciencey. He also didn't get anything, he didn't get his name attached to anything, right? Like Newton, we've got Newton's laws, you've got the apple fall on Newton, and I have all those stories. This other guy didn't. His name was Gottfried Leibniz. He was German. And these two actually both came up with the idea of calculus at the same time. It's because scientists, this was in the 1600s, so the 17th century, scientists at that point were starting to try to answer questions that had never been able to be calculated before. And so these two guys kind of came up with ways of dealing with it. Now, I'm just kind of bringing this up to share a couple of things. First of all, you're going to see a lot of notation that we use in calculus. Some of it is Newtonian, and some of it is due to Leibniz. So there are remnants of both of these guys still around in terms of what we do. I will probably mention them along the way, so I want you to be familiar with them. But a little historical context too. So Newton was English, Leibniz was German. This ended up causing like a big fight, like a huge fight among mathematicians on who invented it. Newton claimed Leibniz stole it. Leibniz is like, oh, Newton, I came up with it on my own. Like, it's fine, you did too. Why are you dragging me through the mud? And what ended up happening was all of the English mathematicians, of course, sided with Newton, and all the mainland European mathematicians sided with Leibniz. And basically, math ceased to advance for quite some time because nobody was communicating with each other. Nobody was willing to share ideas anymore because the thought was, well, the English guys were like, well, geez, if we share with anything with these guys over here, they're just going to steal it and claim it as their own, and vice versa. So it ended up being kind of a dark age in mathematics for a while, which is unfortunate because this thing, calculus, is huge, and it's allowed us to do so much more later. So we got Newton, we got Leibniz. Once the dust settled, everything was great, but for a while, it was kind of gnarly. So let's talk about some of the questions they were trying to answer. So here's the first one. So I've got a pen, nice little whiteboard pen right here. I'm going to toss it up in the air. All right, so here's my question to you. How fast was it going?
-9.
Go ahead, Vale.
I was going to say acceleration, not speed.
Okay. Yeah, I heard you starting to say 9 something. So we do know that there's gravitational acceleration, and the gravitational acceleration in metric, which of course is the only thing we're going to use because metric, is 9.8 meters per second squared. Now, Newton was one of the ones who kind of came up with that idea. So, but that was acceleration, not actually speed. So yeah. Here it comes again, right? Pen, toss it in the air. How fast was it going? All right, so error is just typed in average speed. What if we wanted average speed? How would you calculate that? So error just gives me the shrug. So speed. No, go ahead. Who was that? Is that a Vale?
Yeah, just distance over time.
Okay, so we know that we've got that DIRT formula, distance is rate times time. So rate is distance divided by time. So we could just take the distance traveled and divide it by the time, and that would give us average speed. Okay, so average speed's not that difficult, and we don't need anything new to do it. I mean, you barely even need algebra, right? But, ready? So we're gonna do this. Let's think about speed, vertical speed. Ready? So here we go. I'm gonna toss it in the air again. But I caught it at the same spot. So what was its average speed? What was its change in position?
Negative.
Yeah. So Robert just said 0. That's actually the case. The average speed there was 0. The average velocity, I should say. Because it started and ended at the same place. So its change in distance was 0. However much time it took, well, I don't know, whatever that was. I don't care. 0 divided by anything is 0. But that's not very useful information, right? Because it's not like it was not moving the entire time. There were definitely points at which it had speed. So average speed is great. But what about instantaneous speed? What's its speed right at the top? What's its speed half a second after it leaves my hand? What's its speed right before it hits the ground, right? If we want to know instantaneous speed, we got to kind of maybe approach this a different way. So Aaron says, what if I pause at the top? Okay, so if we were just to look at from here to there, we could definitely get an average speed. If we had a stopwatch and we measured the distance, so we could get an average speed there. And so that's the other issue with average speed is it depends over what time period, right? Are we talking about the entire path from when this leaves my hand up to the top and then hits the ground? Are we just going from when it hits, or from my hand up to the top, some other point somewhere in between? And so average speeds are okay, and they do give us information, but they don't necessarily give us information that is useful. Like in the case of if we did average speed from when it left my hand to when it came back to that same spot, right? So one of the questions that was trying to be answered was, what about velocities? And more to the point, they already knew how to do average. This was easy, right? Velocity, it's just your change in your position. Okay, so I put here delta x divided by your change in time, delta t. Okay, so if you're not familiar with the delta, this triangle right here is a Greek letter. It's the capital delta, and that just means change in. So this is the change in x, and this is the change in t. And so this is just good old position divided by time. And so this is definitely an algebra thing, no problem. So I'm going to put a check mark by that because we already knew how to do this. We being the collective we. Obviously, I wasn't around. I'm not that old. So our average is great, but really the question is, what about instantaneous? All right, so this was the big question. How do we figure out instantaneous velocity? How do we figure it out at any one given point? All right, well, this is one of the questions that calculus was actually introduced to try to answer. So let me kind of show you how this can be approached with a graph. Now, they didn't really think about it, these two guys didn't really think about it graphically. Drawing graphs for math wasn't really a thing yet. That kind of came about a little bit later. But if I draw it as a graph, I think you guys can see it a little bit better and know what's going on. So let me draw a graph here of just position versus time. Okay, so on this axis, we're going to have time. And on this vertical axis, we'll have position. So we've got some sort of a graph that's showing us our position with time. So I'll actually do the pen flying through the air example. It was at a certain height at time 0. Let's say time 0 is when it's in my hand. So I toss it up in the air. So as time's going on, this is going up into the air. And then it starts falling back down until it hits the ground. So you probably learned somewhere along the way that you do get a parabola for the path. You will prove this in physics next quarter. For those of you who are taking calculus-based physics, you'll see why it has to be one. Actually, you'll probably see it next quarter in math as well. We usually talk about that. We might even talk about this at the very end of this class in December. But anyway, it looks something like that. All right, so if you think about it, average velocity, then maybe if we don't want to call it x, we can call it y, because maybe you think of that better as a y. So it's a dy dt. So think about what happened when I calculated average velocity. So in that first example, when I said, what about when it comes back to my hand? I need my change in y over my change in t. Well, here's my change in t. Remember, t is playing the role of x here. And then my change in y was actually 0. So that's why my average velocity was 0. It was 0 over delta t. But let's go to another one. Like, remember when Erez asked about, well, what if we just went to the top? Okay, well, let me put a point up here. So this would be our top. And so now my change in t, again, it's horizontal. It's just this little bit. And there is a change in y. It's this vertical piece. So there's my delta y. And here's my delta t. So think about what average velocity is. It's the ratio of those, delta y over delta t. You know that as something else. Something from algebra was this change in y over change in t.
Slope?
Yeah, it's a slope. That's really just the slope of the line that connects those 2 points. Okay, so what we can tell from this like graphing kind of idea is that this average velocity, or we'll just say velocity, it's actually going to be the slope of the line segment that connects those 2 points. So if we've got a graph of position versus time, and you've got the two positions, if you just look at the slope of the line that connects them, that's going to be your average velocity. Okay, cool. I mean, that is kind of nice, actually. Makes it so that we don't even have to really do anything new. We can just calculate those points and find the slope, and we're good. So you can see why this one, the average velocity was 0. If we catch like at the top, this average velocity is going to be something bigger than 0. Sure, it's going to have greater speed. But check out the way that we define this then. If we were to look at, say, when it hit the ground, we were to look at this one, that one's going to have negative slope. So that would mean that its velocity is negative. And that may not sit well. I know some of you might go, wait a minute, how do you have negative velocity? So here's the deal. There's a difference between velocity and speed. Velocity and speed. Speed is what you think of. Miles per hour, feet per second. Velocity is a vector. You remember vectors, I hope, a little bit? Vectors are things that have not just a quantity, but a direction. And when it comes to velocities, the directions here are up or down. So a positive velocity means it's moving upward. A negative velocity means it's moving downward. So in the case of that pen flying through the air, it's got positive velocity till it reaches the top, and then it's got negative velocity as it's coming down. So overall, in this case, it would end up having negative velocity because it dropped. It started here, but ended up down on the floor. So it's got negative velocity. Okay, so negative velocities are fine. Negative speeds, not so fine. So if you get a negative velocity, its speed is just the absolute value of that. All right, so let me go ahead and write this out because this is a big distinction. And for those of you who have not really done physics, you won't necessarily know this. This is one of those places where science does things a little bit different, names things a little bit differently than regular folk, all right? But speed is actually the absolute value of velocity. Just FYI. So if you're ever doing a problem and they ask you for speed versus velocity, that's the difference. All right, well, as you know what we need to do if we want to find the average velocity, that's look at the slope of that line and those 2 points. Well, let's get back to this question. What about instantaneous? I want to know the velocity at just 1 point, right? I want to know how fast we're going at this 1 point, say, at the very top, or right as we're hitting the ground, or something like that. Well, here was how Newton and Leibniz came up with calculus, or at least the first part of calculus. And they kind of approached it this way. They said, all right, let's say that this is our curve. And so this is position versus time. So I have no idea what might be causing something to move like this, but let's just say that's what's going on. And we want to find out the instantaneous velocity at this 1 point. Now, that's kind of impossible to do. Because think about how we defined velocity. It was the slope of a line. And 1 point does not make a line. You got to have at least 2, right? So here's what they did, though. They said, well, obviously that 1 point's not good enough. So what if I were to be just off a little bit? Let's say we're over here. I can connect these 2 dots and make a line. This would give me an average velocity. And that average velocity is going to be an approximation of the instantaneous velocity, right? It's not going to be the exact velocity, except in some very rare cases, but it'll be close. So it's a guess, and it's a decent guess, but what we want to do is make this guess better. Well, the idea then was, how about we move it closer? Instead of taking this bigger gap, let's go with a smaller gap. This is still going to be an approximation for the instantaneous velocity, but it's a better approximation than the first one. Okay, so that red line segment, its slope isn't as close to the instantaneous velocity as that of the blues. All right, well, then keep going with this process. Bring it closer still. Okay, so let's bring another point right there. So we're shortening that time period. And this is giving us a better approximation for the speed. Now, if you're looking at this graph and it's still kind of like, I don't know why this is helping, go back to the idea of the pen going up in the air. And I say, I want to know the instantaneous velocity right as it comes back and lands in my hand. Okay, so right as it comes there. So I've got my stopwatch. I know I'm going to end my stop at, or I'm going to stop it as soon as it hits my hand. But if I've got a really long time period, there's a lot of chance for this velocity to change. If I shorten my time period, the velocity is going to be more consistent over that smaller distance. And so that's kind of the idea, is that if we shorten the amount of time or the amount of distance over which it's traveling, the better this approximation is. All right, so in essence, what we're doing is we're bringing that second point really, really close to the first point. And if they're not the same point, I can still find the slope. But I just want those 2 points to get so close together that they act like 1 point. All right, well, this is what ended up happening. All these line segments right here are what we call secant lines. So just some terminology here. Yeah. This actually comes from circles. If you've got a circle, any line that intersects the circle in two places is a secant line. If you have a line that intersects a circle at just 1 point, think about that look like. If it just intersected at 1 point, it would have to just sort of skirt it. This is what we call a tangent line. Well, all of the line segments are secant line. And so this is your average velocity. It's the slope of these secant lines. For the instantaneous velocity, it's the tangent line slope. So in essence, this is what calculus was invented. It was invented to figure out these instantaneous velocity, which so means the slopes of tangent. And for us, we live, obviously not all of you are in Tahoe, but the majority of you are. For those of you in Tahoe, tangent lines are really easy to picture. Just imagine your snowboard or your skis up on the slopes, right? Your snowboard doesn't actually touch the ground all the time, right? Like think about when you're going over a little hill or something. But your snowboard is a tangent line. It is touching that hill just in one spot. So imagine that this is one of the runs up at Heavenly, and think about what snowboard would be doing as you're going down it, right? Your snowboard would be pointing in this direction. And as you go down the hill, it would kind of do this, right? Well, your snowboard is a portion of a tangent line. The tangent line to the curve that would be the hillside. Where that analogy breaks down is when you're down in the dip here, because now the tangent line would be underneath, And if your snowboard looks like this, you have big problems. All right, you're buried in the snow and you're face planting and all that good stuff. All right, so this was the first question of calculus, or the calculus addressed, was how do we figure out instantaneous velocity? It turns out that this is actually much bigger than just velocity. We use this for any time we're looking for a rate of change, right? Velocity is a rate of change. It's a rate of change in position with time. But if we want to look at the rate of change of anything, the change of income with time, the change of temperature with distance, whatever, those all led to the same kind of question, right? And so the tool that was developed is what we call a derivative. All right, so this is the actual thing that we're going to use here in math to calculate. This is a derivative. So what it is it's an instantaneous rate of change. You can also think of it as the slope of the tangent line. And we'll talk about how to do this in a little bit. We have to get some tools before we can actually calculate derivatives. But this is primarily what we're going to do this quarter. All right. And so this branch of calculus is what we call differential calculus. Because there's another branch that comes from answering a different question. But I want to do an example of this just so you can kind of see how this plays out. All right, so we're looking for instantaneous rate of change, and it's the slope of the tangent line. So let's take a specific function, and let's see if we can approximate the slope of the tangent line, kind of using the approach that I just illustrated, taking a step away and then shortening that step. So, for example, let's look at good old f of x equals x squared. You should all immediately be able to picture that, know exactly what it looks like, how it behaves, and everything. Okay, and we're going to see if we can figure out what is the approximate velocity at x equals 1. All right, or approximate derivative at x equal 1, or approximate instantaneous rate of change at x equal 1, or however you want to think about it. All right, so here's our graph. Again, you all know it. It's one you know and love. And it's just a good old happy parabola, something like this. And we're over at 1. Right, so this point is 1, 1, and I want to know what's the approximate velocity. So we're looking for the slope of the tangent line at this point. And the tangent line looks something like this. This would be the line that hits this graph just at this point. Again, think about skis on the mountainside. I literally use my pen. You can use your pen or your pencil to do this well. Just imagine here on this graph, at some point, set it so that the pen or pencil just grazes it. And then as you move along, you can kind of your tangent line. Okay, so that's my tangent line moving along as I go to different places. So here's what it would be for that point. Okay, so I'm really looking for the slope of that line, but I don't have another point on that line, so that doesn't really help me there. So what we'll do is we'll make some secant lines, and we'll use that to figure out our slope. So what I'm going to do is make a little chart over on this side that has in it delta x, delta y, and then m for our slope, okay? So the first step I'm going to take a step of 1 in the x direction. So that means on my picture here, somewhere over there is 2. So here's my step of 1. So I need to get my change in y, which is going to be how far up here do I go until I hit my parabola again. All right, so how much further up do I go?
7 because 2 cubed is 8.
Okay, so let's go to the x squared. So 2 squared is going to be 4. So up here, I'm at the point 2, 4. So my change in y is actually 3. And so what we get then with our slope is change in y over change in x is 3. So that one's got a slope of 3. And what do you think? This line segment that connects this blue dot with black dot, so I'll go ahead and draw it in here. Is its slope bigger or smaller than the slope we're looking for?
Bigger.
Yeah, it's going to be a little bit bigger. Right? It's a steeper line. So the actual velocity at that point has to be less than 3. How much less? I don't know. We'll figure that out in a minute. Well, let's shorten that step. Instead of going out 1, let's just go over 1/2. So now, somewhere here is 1.5. And we're going to connect those 2 points and find its slope. Again, from my picture, it looks like that slope is going to be bigger than the instantaneous, but it's getting closer than the blue one. So whatever answer we get here should be a little bit better. All right, so now we got to get our change in y. Well, let's figure out where this point is. So 1/2 we have. If square that, I get 9/4. Let me actually write this as 3/2. A little bit easier, right? So we got 9/4. So we go from 1 up to 9/4. That change in y is 5/4. So if I want to calculate my slope, I do change in y over change in x, which is 5/2. So it's a smaller number, which is good because we see that its slope isn't as, or this line isn't as steep, and it's getting closer to what we want. All right, well, let's make that smaller still. How about this time? We make that step 1/10. So that means there's another point in here. I have to exaggerate it a little bit, but that's 1 1/10. So let's call it 11/10. When I square that, I get 121/100. And no, you don't have to keep it as fractions. You can go to decimals. But now my change in y is 21/100. So I take 21/100 and I divide by 1/10. I get 21/10 or 2.1. You can use your calculator to check me on, which would probably be a bad idea because someone's in the morning, my brain's not quite firing on cylinders. Okay, took a tiny step at 2.1, which shows this is still going down. Okay, well now let's take a really tiny step. Let's take a step of like 1/1000. So that's so close, I wouldn't even be able to show you separate dot. So we're going to take 1/1000. So little tiny step. Okay, so then the question is, is my change in y? Well, my y, if I were to calculate that, I would have to take 1001 1,000ths and square it. And then subtract 1. And I don't actually happen to have a calculator on me, so I'm just going to slug it out real quick. So 1,001 times 1,001 is going to be 101, 101 over 100,000. When I subtract my 1, this ends up being, oh no, I did something wrong there. Hold on. I'm trying to go too fast. There it is. Okay, so we get this. When I subtract off my 1, that ends up giving me 2001 over 1,000, so 1 million. When I divide that, delta y by this delta x, I get 2.001. So all this calculation stuff, just don't worry about it. The more important thing is this is my change y. When I divide it by that change in x, I get 2.001. So it went down again from 2.1 to 2.001. But that was like a little teeny tiny step, right? And I get a number just slightly bigger than 2. Well, it turns out that the slope of that secant line is 2. Like it has a value of 2. We'll see where that comes from next week. But just this process allows us to start seeing approximately what that slope is. And the smaller that step, the better the approximation. So this is the idea behind what Newton and Leibniz did. And we are going to expedite this. We're going to make this so much faster. I know right now you're probably looking at this and going, oh my God, this is going to suck so bad. No, well, it does. It sucks doing it this way. But mathematicians, being who we are, yeah, okay, this is long, this is boring, this is lazy. Let's figure out a better way. And there is a better way, and I'll do that to you next week. But this is how it progressed, all right? This is how we got where we are. All right, so this is differential calculus. It's basically looking at slopes. It's not really that bad. And what I tell people all the time is that calculus isn't hard. And they usually chuckle when they go, of course you say this because you're a math guy. But it really isn't. Like calculus is finding slopes. How about this? What if I was going to give you a test on pre-calculus? Okay, and this is going to give you your grade in calculus. Don't worry, I'm not going to do this, but suppose I did. You'd probably like it to be like half finding slopes, right? Finding slopes between 2 points and stuff like that, that's easy. That's way easier than doing, proving a trig identity, converting logs to exponents. Like slopes are easy. So the idea behind calculus is really basic. It's not that complicated. And once we get the tools for doing this faster, it really is way less complicated. So hopefully this lives up to that you guys, as you go through calculus, will agree with me that calculus itself is not difficult. The algebra
Even as
stuff,
we go further? Even as you go further,
calculus is not going to be the problem. It's going to be algebra that's the problem. For like just about every single one of you I see on screen, and I know I only know like half of you. And trust me, this isn't, Vail's going to have problems because I know Vail's. No. This is just reality. Every time I calculate, it's the algebra that makes people stumble. The calculus is fast. You do it like nothing. It's the algebra that'll get you. So on that happy note, let me show you the second question. that calculus was used to answer. So it's a simple, really easy question. I'm going to give you this shape. All right, so see that shape right there? Kind of looks like a kind of weird crown sort of looking thing. What's its area?
It's going to be close to the rectangle.
Easy question, right? Okay, it's going to be close to a rectangle. Had I given you a rectangle, you told its area.
You didn't give any numbers, so no.
You guys know how to calculate the area of a rectangle?
Length times width.
Yeah, so if we just have a rectangle, and that actually doesn't look much like a rectangle to me. Okay, so if we could calculate, if we measure, say, its length and width, if we had a ruler or something, we measured those, then the area is easy enough, right? This one is just length and width. This shape, however, not a rectangle. And I was actually pretty nice. I gave you this shape because it's almost a rectangle. What if I had given you a shape that looked like that? Yeah, it's way less rectangular. All right. So maybe a trapezoid. All right. So maybe I need to get something that definitely doesn't look like anything you've ever. Okay. So how about that area? Okay. So the next part of calculus really came from trying to calculate areas. How do we figure out areas of shapes that are not nice? And when I say nice, I mean ones we already have formulas for. Triangles. I'll even throw in circles, even though that's kind of cheating, because to actually know the area of a circle, I know you all know it, right? Pi r squared. To actually know that, you need calculus. You'll learn through the course of this year where that formula comes from. Area of a circle is pi r squared. Actually, you know what? I'll show you how the circle was determined, because it was really figured out before calculus, as we think of it, was invented. But it uses calculus ideas. But anyway, that's the question. How do you calculate these areas? So this was a thing that they were interested in back there in the 17th century. And when I first said, what is this area? I think it was Vail who said, like, well, it'll be close to the rectangle. And they realized this. Hey, you know what? That's true. What if we have rectangles? We approximate it with rectangles. So like we could do one rectangle here and maybe make it something like that. And the area of the blue rectangle is going to be pretty close to the area of the shape that we were given. Yes, there are bits of this shape that are outside the rectangle, areas we're not accounting for, but there are also pieces of this rectangle that are outside of the area, and the bits that are overlapping that we're missing, and they're probably pretty close and are going to kind of even out. But when you get something more complicated, like this funky shape that I drew over here, it actually kind of starts looking like Wu-Tang Clan something. This one, draw a rectangle that's approximately that area. That's a tough question, right? So this is actually what they did. They said, well, instead of thinking of it as one big rectangle, what if we think of it as a bunch of little rectangles? So what I'm going to do is split up. Take this horizontal line and let me split it into some pieces. I'm going to make mine all the same width. They don't have to be the same width. basically said, all right, let's just form a rectangle in each one of these. And we'll make it so that this rectangle in each of these regions is approximately the area of the shape in that region. So I don't know if you can really see this on the video. I hope you can. But if we just looked at these red areas, those red areas fit this curve better. There's less overlap. There's less gap, right? Like think about this huge chunk that we had missed, or we were counting in the area of the rectangle that wasn't actually there. Most of that is now gone because inside those red rectangles, there's very much less area that we're accounting for that didn't exist. And the same thing for bits that were being missed. So this is a better fit. And we went, well, what if we break it down even further? So I'm just going to divide these in two. So we'll use green this time, but do kind of the same thing, but make the areas, the rectangles, that much smaller. And if you were to look at the green ones fit it still better. And they realize that if we just keep doing this more, have more smaller rectangles, that eventually we start getting a really, really good approximation for that shape. So even something fun like this guy, literally what they did was they cut it into vertical strips. And each of the vertical strips, they approximated with a rectangle. So maybe here is the rectangle for this approximation. And there's a rectangle for that approximation. And there's a third rectangle over here, right? And these areas are easy to find. Then you just add them all up, gives you an approximate value for that area. Okay, so a completely different question, right? This is a completely different question, but it still is related to the other part of calculus. So the tool that we use for this one is what we call an integral. And so this is the other part of calculus. This is called integral calculus. Okay, so we use a thing called an integral figure. And what this does is this finds areas. Turn out the integral for way more than just finding areas. And I'm going to go ahead and tell you this. Really what it is, the special case, real integral do, they add up lots of really small things. And I do mean to be vague here when I say really small, so say things. This big more than there. But in this context, think about what am I adding up? Add up areas. That's my thing. And they're really small because I'm going to make these widths really small. I want to have tiny little strips. The of those areas is really small amount, but lots of them. All right, well, integral calculus, you're going to learn about this next quarter in 6. That's the concentration quarter number 2. Or quarter number 1, our quarter is differential calculus. And just a slight spoiler, it turns out that these two things are related to each other. Finding areas and finding slopes, super related. All right. Anyway, So there's a little preview of calculus. In terms of this area thing, let me show you an example, and I'll tell you how we figured out the area of the circle. At least let's figure it out a couple thousand years ago, not just a couple of years ago. But let's go back to X again. But this time, instead of looking at a slope, I want to look at an area. And again, let's say we're going out to 1. I want to find the area of this region. Regions under X squared, but above the x-axis between 0 and 1. So something should be able to tell me right away is you know that it's less than 1. Are you guys confident with that?
Yeah.
Because think about just if we were to take square by 1 square, have an area of 1, which is way bigger than this little. So it's less than 1. In fact, you should probably also be pretty confident that it's less than 1/2. Because if I were to draw this triangle, its area is 1/2 base height, so 1 times 1/2. So we should expect that that area is also something or half. But how exactly? I don't know. How exactly? So here's what we're going to do. We're going to make an approximation. And we're going to do this by splitting this into 4 chunks. And what I do is I'm going to build rectangles such that the heights of the rectangles are from the right of the endpoints. The right endpoints of the interval. So I'm going to run up from these function, run over and get a height. So those 4 rectangles, when I add up the area, it's going to be too much, right? It's going to be a little bit too big, but at least I know that an overestimate of the area, and it's going to be a pretty decent overestimate. All right, so here are what the different heights are for this. The tall, of course, has a height of 1. So I'm going to put a 4 in there so that we can label our areas. 1, 2, 3, 4. So for area 4, its base is 1/4, and its height is 1. So we get 1/4. Okay, 3 is a little bit more difficult. Its base is still 1/4, but its height, if we get this is 3/4, right? So in terms of its height, it is going to be 9/16. So that's going to give me 9/64. If I go to number 2, its area, again, its base is 1/4. 1/2 when I square it gives me 1/4. So height is 1/4. So that's 1/16. And then number 1, its width is 1/4. Its height, if I take 1/4 and I square it, I get 1/16. So 1/16, which is 1/64. So the total area then, I just add these here. So these two, the first and the second, will give me 64, which is 5 30 seconds. We get another 2 30 seconds, 7 30 seconds, plus another, I believe this is 15 30 seconds. He says very confidently. All right, this is an approximation for what area is, 15 30 seconds, which is under 1/2 which we definitely agree is reasonable, but it's definitely an over guess. Now we could make a similar under guess by, instead of making these rectangles, what if I made green rectangles that sat underneath her, the left points? So now we're going to get this area. So we could do the same sort of thing. And here's really nice. When we go to green, notice that this green rectangle is the same size as the second biggest. So if we number these for the greens, the first one doesn't exist anymore. But this is the fourth one, this is the third, and this is the second one. And the first one, if we were to go to a 1, its base is 1/4, but its height is 0. Actually is no area there. So if we were to add up all the green ones, so the green total, this is going to be 9/64 plus 1/16 plus 1/64. That was these three values plus 0. Which I'm pretty sure is 7 seconds. And so that's a under guess. So long story short, that area we were looking for is somewhere between 7/30 seconds and 15/30 seconds. We were able to get a prediction by just using 4 rectangles. As were already easy to guess. Now, if we wanted a better estimate, if we wanted to shrink this interval, all we'd have to do is more rectangles. I don't do it right now because I'm lazy, basically. Okay, instead of 4, if we have 10, what if 100? What if we have 1,000,000? Nobody wants to do a million rectangle now. Calculus lets you do that. Lets you add up those million rectangles and then some. All right, so this is the idea behind integral calculus. This idea, this example of finding an overguess and an underguess, then you make a better by smaller or better estimation. It's actually called the method of exhaustion. I love that name because it is exhausting. We only did 4. Imagine doing this 100 times. But this is actually how the area of a circle was first figured out. So let me just show you this real quick. And again, this is more just for your information. You don't need to know this for a test or anything like that. I just think it's good to see where these things come from. So here's a circle, and I want to find its area. So I know that you have to do is figure out the radius, square it, and multiply it by pi. And this was first trying to be figured out. That was known. So another guy, another huge mathematician, this guy was Greek. His name was Archimedes. You've probably heard of him. He's got all kinds of funky stuff attached to him as well. Easily, again, like Newton, easily in the top 3-4 mathematicians of all time. Right? But he actually was the first one to come up with the idea of the area of a circle. And this is what he did. He started by saying, well, let's fit shapes in here that we know, like a triangle. So we're going to get an equilateral triangle that fits inside the circle. We can calculate that area pretty easily. We know that the circle then has an area bigger than that. And he said, well, okay, that's a circle, but what if we made it better? What if we went with a square? Let's find the biggest square that fits inside that circle. It's going to give us a better approximation. Well, then after a square, of course, comes a pentagon. We'll see if I can actually draw a pentagon here. Yeah, that's not terrible. So go pentagon. That fits better. Well, then what comes next? How about a hexagon, septagon, octagon, nonagon, decagon, and so on and so forth. And every time we add more sides, we get a better approximation, right? So here's going to be one in red that's got just a whole bunch of side lengths. I have no idea how many this is. But again, this is a polygon. It has lots of sides. But if you calculate the area of that polygon, it's going to be much closer to the area of the circle. So we just keep increasing the number of sides, and it gets closer and closer and closer to giving us the area of the circle. All right, now these are all under guesses. So then he went, well, what about over guesses? Do the same thing. Start with a triangle, an equilateral triangle that fits outside of it. Clearly, that's going to be too big. So we make a square that fits inside of it, or the circle fits inside of. Less of an overguess, then a pentagon, then a hexagon, then and so on and so forth. And so this is actually how thousands of years ago, I mean, think about this. The area of a circle has been known for thousands of years. This is how they figured it out. The Greeks are really in geometry. They love geometry. And so for them, this was no big deal. But it got them to a point where they understood circles and their areas. And therefore, they also had a really good estimate for pi way back then. Right, guys? Pi 3.14159. We have millions of digits because of computers. The Greeks are many places as needed, though they have decimals. They didn't. So it's really old, but Newton and Leibniz more recently came up with a system of living that we still use today. So a little review idea of calculus is answering these two questions. How do we find slope? And how do we find areas? Again, not hard concepts. Calculus is hard, I promise. It's a nitty-gritty stuff to do to get there. That's going to be difficult. So speaking of, since we're still a little bit behind schedule, let's start working on these ideas that are going to lead us to calculus. So the first thing I'm going to do is I'm going to introduce you to a new kind of thing called a limit. Now, first of all, the notation for limit. You're going to see LIM. That makes sense, right? It's limit. Now, underneath the limit, what you're going to see, I'm going to do this generically, but you're going to have your variable, in this case x, and then there's going to be an arrow. And that arrow is going to point to a number. So right now I'm using C, but realize that this is a number. Where this is going to be the variable. So it's always going to be variable with an arrow and then a number. And then we're going to have our function. So this is the notation you're going to see. And the way that we say this in words is this is the limit as x goes to C of f of x. So that's phrasing. the limit as x goes to c of f of x. There's our generic. Let me give you a specific just so you can kind of see what you'll really see. An example would be something like the limit as x goes to 2 of x squared minus 1. So we've got a function, x squared minus 1, and we're looking at the limit as x goes to 2. All right, so that's what you're going to see. But of course, it doesn't answer all the what does that mean? What the hell is Bruce even talking about when he says limit as x goes to 2 of x squared minus 1? Okay. With functions, you're really used to you plug something in, you get something out. Right? That's how functions work. That's what you do. Well, now we're concerned with the function value at a point. We're concerned about the function's value when we're near the point. Okay, so basically what this is saying, if you wanted to translate what this question is actually asking, it's saying, what value does the function approach as x gets close to? It's limit. It's not asking what does the function equal at 2. That's not what that's asking. This is instead asking what is this function getting close to when x gets close to 2. So it's kind of a big difference, right? If you want to know what happens to the function at 2, you would say this, right? This is what is the value of the function at x equals 2. So real function stuff is what's going on at that point. Limit are what's going on close to that point or near that point. So whenever you take a limit, you don't actually care at all what's happening at the specific number. What you're concerned with is what's going on near that number. So this is the idea behind a limit. Let me show you how we can get approximate values for these. So we're going to learn a couple of things. One, we're going to learn how to actually evaluate a limit. We are going to learn about that. But we're also going to learn how to approximate it. We're going to learn how to approximate it 2 different ways. One is just by plugging in numbers and seeing about a pattern. The second is by drawing the graph. We're going to look at the graph and see if we can use that picture to help us see what's going on. But those are just approximations. Those give us an idea. But we're also going to learn how to actually know. So we'll use algebra to help us there. But let's start with an example of one. It's not a super complicated function, but it's one that you'll see why I choose it here in a second. So let's look at this. Let's look at the limit as x approaches 1 of x squared minus 1 over x minus 1. So we're looking for what happens as we get close to 1?
Wouldn't it be 0? Because if you plug in x,
Okay, so Suzanne, you should just said, well, wouldn't it be, should I say this right? Wouldn't it be 0 because you plug in x, and I think you meant 1 for x, right? So if we plug in 1, don't we get 0? Okay, I'm actually kind of glad you went there. You fell for the trap. You totally fell for the trap, and don't feel bad about this because I set this trap every time I teach calculus, and everybody always steps in it. All right, think about what Susan just said. She said, well, we get this because when we begin 1, I don't care about 1. I don't care about 1. I care about when I get close to 1. So you can tell me, hey, let's see what happens when we plug in 0.9, 0.99, 0.9 with a million nines. Okay, that's relevant to the discussion. But if you say, well, let's plug in 1, I'm going to stop you and go, wait a minute. I don't care about 1, right? If I want to plug in 1, think about what I'm doing. I'm doing f of 1. But remember what I just wrote over there? That is the value of the function at 1. But that's not what a limit is asking. The limit is asking what happens when we get close to 1. Okay, so please don't feel bad about that, Suzanne. I'm glad you went there, because if it wasn't you, somebody was going to say it, right? Someone was going to say, hey, plug in 1. But this is a big difference. And I know this is brand new to you guys. A lot of you have never ever seen a limit before, or the idea of a limit. So it takes a little bit of just getting used to, because we really are used with functions to just like, yeah, you plug in the number. With limits, we got to approach that number. Okay, so f of 1 equals, and I'm going to put don't care. I mean, frankly, I don't. I don't care what happens at 1. I want to know what happens when I'm near 1. So let's see if we can get an idea of what's going on with this function when we get close to 1. So I'm going to make a chart again, good old T-chart like we're used to. And so I'm going to plug in numbers that get closer and closer to 1. So none of these are 1. None of these numbers is actually equal to 1, but they're getting close. Right? 0.9999 is awfully close to 1 and probably closer to 1 than you think is necessary. Right? But let's just see what happens when we plug in those different values. Okay, so this is where we want to crack out our calculator. It can help us out. I've already done this, so you can just trust me. Famous last words, right? I use a calculator to check it. But you take 0.9. Let's take 0.9 and plug it in. So you're going to get 0.9 squared, 0.81. Subtracting 1 gets you a negative 0.19. 0.9 minus 1 is negative 0.1. You do that division, and you get 1.9. Okay, so when I'm at 0.9, which is kind of close to 1, I get 1.9. So do it again. Take 0.99. So 0.9 squared minus 1, divided by 0.99 minus 1. You get 1.99. The next one gets 1.999. And this fourth one on my list gets us 1.9999. At this point, sometimes people will say, is it coincidence that we're just getting 1 plus that? My answer to that is no. That's kind of how this one works. But it doesn't always work that way, so just be careful when you plug stuff in. Just use your calculator and trust it to give you the right number. So looking at this, what's happening to our function? What's happening to approach? We get closer and closer to 1.
2.
Yeah, so they get closer to 2. I bet it doesn't surprise you that if we were to add 1, 9, that's x, we just add 1, 9 on fx. But it definitely looks like getting closer to 2. All right. Now, this is what's going on when my x's are smaller than 1. But what if they're bigger than 1? Because notice that this statement right here is just saying I want my x's to be approaching 1. It doesn't say from smaller or bigger. So let's do the same thing, but with numbers that are getting closer to 1, but from the other side. So we'll do 1.1, 1.01, 1.001, 1.0001. So again, punch those in your calculator. You get 2.1, 2.01, 2.001, 0.0001. And you approach from the other side. Does it look like we're getting closer and closer to 2? Yeah, I see a thumbs up. I see Bob. Yeah, it looks like we're getting close to 2. So what I'm going to write is that this thing, as we get closer and closer to 1, it looks like it equals 2. But because I don't know for sure, I mean, I've got some good evidence, but I don't know for sure, I am going to put a question mark above for now. Okay, I don't know that the limit is 2, but it sure feels like it. I am going to warn you, though, and you probably have seen this in math, sometimes what it feels like, sometimes it should be, is not what it is. So just going to warn you that will happen here with limits as well. But there's also that saying, right? Like if it looks like a duck, if it walks like a duck, if it quacks like a duck, it's a duck. Same kind of thing here. If it looks the limit 2 coming from both sides, it probably is 2. Right? So I'm going to put equals 2 with a question mark because I feel like it might be. But notice again, I never once plugged in 1. I don't care what happens at 1. I care about what happens near 1. And in fact, what happens if we actually plug in 1? Right? Suzanne, when she first said get 0, turns out it isn't, though. Check this out. If you do from 1, 1 squared minus 1 over 1 minus 1, which is 0 divided by 0. And 0 divided by 0 is this horrible thing. It's not really horrible. Like it's weird. But it's what we call an indeterminate form. Meaning we don't know what it is. 0 divided by 0 can actually be anything you want. It could be 37. You can see your faces right now. I think some of you can see other people's faces. As soon as I go, hey, 0 over 0 can be anything, including 37, most people are like, no. Because 0 divided by anything is 0, right? But what happens if you divide something by itself? Well, then you get 1. Yeah, okay, but then what happens if you divide by 0? You can't. Right, so all of a sudden we start running these problems. Check this out. Let me show you why 0 over 0 could actually be anything you want. So 0 over 0, let's just say that that equals x. Right, so the question is, what do we get when we divide? Well, you remember how you check, right? You check division by multiplying. So this is basically saying, all right, we need some number that when we multiply it by 0, gives us 0. So what number can x be?
All real numbers.
Yeah, it can be anything you want, including 37. 0 times 37 is 0. It could be -6. 0 times -6 is 0. It could be 2. 0 times 2 is 0. Ugh. Okay, so that's what I'm saying. 0, 0 is kind of a gnarly beast because we have no clue what it is. It literally can be anything. But don't bother plugging it in. Doesn't matter. We want to know what happens near that guy. Okay, so one thing you can do is literally plug in points that get closer and closer and closer to your value. Okay, well, I'm going to go ahead and show you graphically how you can do this as well. So I'm going to share my screen here from my other computer. And we'll go to Desmos. Desmos is my favorite graphing program online. I don't know if you guys have ever seen Desmos, but it's desmos.com, so dsmos.com. It has kinds of things, but we're just going to go to the graphing here. And when you graph, it's super nice. It allows you to graph in all the different ways, including things like polar and parametric, wacky stuff. And we're going to go with y equals, and we have x squared minus 1 divided by minus 1. Okay, so here's a graph of x squared minus 1 over x minus 1. Kind of like a line, huh? Well, here's what we could do if we wanted to get an idea of what value this function is taking on as we get closer to 1. So here's x equal 1, right? It's halfway in between these two. So imagine that you're a spider walking along this line. And we're going to move towards 1, meaning we'll move to the right until we get closer and closer to where x equals 1. So if I'm following my graph, if I'm the spider walking along it, okay, now I'm up here to x equals 0. And I'm going to get, there's x equals half, x equals 3/4, x equals 0.9, 0.99, 0.9999. My y value, right, think vertically, my y values get closer and closer to 2. Similarly, from the other side, if we're walking towards x equals 1, we're walking to the left. So here's x equals 3, x equals 2, 2.5, or sorry, 1.5, 1.1, 1.101, 1.01, 1. Blah, blah, blah. I'm getting closer to this. So if both sides start putting this y value, that there actually is no Desmos isn't smart enough to show that. No matter how much I zoom in, try to zoom in here, and we're looking near x equals 1. That's right there. Zoom in a couple more times. So I don't know if this there's 0.9, 2, 2.1, 0.9, 1.1. So it looks like everything is good. It turns out there's just one little hole. Little graph has to be where we're looking. All right. So you can always use a graph to help you figure out your limits. So let me do this. Let me come back to the regular screen, and I'm going to change the function because this one's a little bit more exciting. All right, look at this guy. This is 1 over x. And what I'm going to do is look at a limit as we approach -2. I'm going to go ahead and write some whiteboard. I don't know that you'll see the in the screen, but we're looking at the limit as x approaches -2 of x squared minus over x. So with our calculator, we could go ahead and start plugging in numbers near -2. I'm not plugging in -2. I don't care about -2, but I want to be close. -2.1, -2.01, -2.0, and so on. On the graph, we're approaching x equals -2. So again, imagine that we're walking on this spider, and we keep moving to the left until we get close to -2. So that's going to bring us right about here where my arrow is pointing on the graph. So my question is, what is that y? Ballpark.
-1.5.
All right, so it looks like it's right around -1.5-ish. And notice that if we come towards -2 the other way, we're spider walking, we start approaching that same, so it's like around -1.5. Let me zoom in one more time here. Oh, get back over to 2. Okay, so there's -2. And it looks like it's around that point, which if we run over to the side here, it looks like -1.5. So again, from this graph, it looks like, so I'm going to put equals a question mark. It looks pretty much like it's -1.5. So that's what we do graphically. We just basically keep zooming in, keep looking as we get closer and closer to that value, and see what we get. All right, well, let me show you one more here. And this one, we're looking at what is the limit at x goes to 0 of the absolute value of x divided by x. Again, I don't know if you can see that in the little screen. It's the absolute value of x divided by x. So I'm going to go ahead and change this so that with the graph. In Desmos, if you ever want absolute value, you can type abs. And it will give you the absolute value. Okay, so this is the absolute value of x divided by x. So take a look at that graph. And again, think about what we're doing. We're looking to see what happens we approach 0. So we're a little spider, walking along, moving towards 0, coming from the left. What value does it look like we're getting? Y. About -1? Yeah, sound good? So Val just threw that in. So it looks like that's approaching -1. Now, what about from the other side? So we're up here. We're walking. What value does that look like? Okay, so a bunch of you're throwing out 1. Okay, so I guess at this point, we're going to say this equals -1 or 1. Put a little question mark over it, though. Well, this is a problem. Because limits, we have an or. There has to be a number that we're approaching. So this is a bit of an issue. But notice that if we had just been coming from one side, it really would have been fine. Like if we're coming from the left, yeah, it's -1. If we're coming from the right, it's +1. It's the fact that they're not the same both directions that's a bit of an issue. So mathematicians have a way of dealing with this. Let me stop sharing. We'll go back to the whiteboard. So first of all, because of the fact that this thing is -1 or 1, what we say is that the limit does not exist. And on Monday, we'll talk about limits not existing because there are lots of reasons for that to happen. But this limit itself doesn't exist because of the or. Because of that word right there, the limit does not exist. So here's what mathematicians did. They said, well, maybe I only care about those one sides. Maybe I only care about as I'm coming from the left or from the right. So they created what are called one-sided limits. And so for those, they use the same kind of notation. They just put as a exponent either a plus or a minus. And that basically tells you which direction to come from. The plus, this means coming from the right. You're coming from the positive side of the real number line. The minus means you're coming from the left. You're coming from the negative side of the real number line. So if we go back to this specific example, the absolute value of x over x, we can now look at the two one-sided limits, and we would write like this. So the limit as x approaches 0 from the left of the absolute value of x over x is equal to -1. Because you may remember on that graph, when we had numbers that were smaller than 0, the y value was always -1. If we come from the right, so the limit as x goes to 0 from the positive direction, from right, absolute value of x over x, that equals +1. So one-sided limits are really the same idea. It's just now we're only concerned with numbers bigger in the case of plus, or numbers smaller. All right. So I know it may probably feel a little bit weird because these are brand new. Actually, I'm not over here. I'll talk about this. These are brand new. We've never seen them before. But we will talk more about them, and we use them a lot in calculus, like all the way, even second year calculus right now, and got limits on Wednesday. So limits go away, but you become more comfortable as we go, I promise. All right. So a couple things. Don't get your first homeworks are due Monday night at midnight. We'll only end on Monday, so there will be a chance to talk, kind of hanging out there. So you can reach out to me, email or messaging me through whatever means, and I'll get back to you when I get a chance this weekend. Other than that, anything else anybody wants to share before we sign off this morning? All right. Monday night at night, Aaliyah. So Monday at midnight. I'm going to go ahead and pause the